Okay, I want to talk about bonds in chemistry a bit. We have different types of bonding. Uh, One type of bond is covalent bond, and some molecules will be formed, and we have some molecular compounds. Other types of bonds are ionic bonds, and of course we have metallic bond. And another type of bond is coordinate covalent bond. Coordinate covalent bond. Okay, I want to explain a bit about these different types of bonds in chemistry. Uh, let's talk about ionic bond first. Ionic bond is formed when we have a strong acid combined with strong a strong metal with a strong non-metal. For example, sodium becomes ion and it gives the electron, and the non-metal gains the electron to be an anion. So if these ions will form a very large, this is the positive ion Na plus, and this is Cl minus, which is chloride. So every sodium ion will be covered with 6 chloride ion, four, two at the right and left, two at up and down, one at the front and one at the back. So we'll have a very large network, or it is sometimes called giant ionic compound. So this ions will continue one after the other. This is sodium ion, this is chloride, and this is chloride, this is sodium ion, and this is continuous. So it will form a giant ionic. It will form a giant ionic lattice. That it is composed of positive ion and negative ion, one after the other. What factors affect the boiling points and melting points of these compounds? One of the items affecting the energy of this lattice is size of the ions. Size of the ions is important. One of the other factors affecting the energy of this lattice is charge of the positive ion and negative ion, of course. Among these two factors, charge is more important. For example, if we have KCl and KBr, both of them has a strong metal, it is potassium, and both have a strong non-metal, which are halogens, chloride and bromide. But we know that down the group, in halogens, the atomic radius increases, so the radius of chloride is less than the radius of bromide. So if we want to draw a lattice of ionic lattice like this, Cl minus ions or chloride ions will be smaller. So because chloride ion will be smaller, the energy will be higher, or it is based on Coulomb's law. F equals K Q1 Q2 over R squared. These positive and negative charges attract each other more strongly because the radius is smaller, So the distance between opposite charges is smaller, so the force is stronger. The force is stronger, so boiling point is greater, melting point is greater. It is more difficult to separate the ions, so we can say bond energy will be greater. So generally I can write down, the smaller the size, the greater the bond energy. The greater the energy. I can say the lattice energy. Okay, what about the charge? Of course, it is clear from this formula, Coulomb's law, that the greater the charge, the attractive force will be greater. The attractive force will be greater, so it is again more difficult to separate the ions from each other. So melting points and boiling points will be greater. For example, if you want to compare magnesium oxide with sodium chloride, magnesium oxide will be greater in melting point and boiling point because the charges here are positive 2 and negative 2, so the force will be greater, and therefore the lattice energy will be greater. So let me write down this as a note. The greater the charge, the greater the charge, energy, the greater the energy, the greater the lattice energy. Of course, some questions may arise here that we were asked to compare the melting point and boiling point of some ionic compounds. We can do the same procedure. For example, if the question says compare the melting points, think of NaCl and KCl. Okay, we can say, okay, anions are the same, but cations are different. Which one is smaller? NaCl is smaller. Because NaCl is smaller, it has a more lattice energy, so lattice energy is greater, so melting points and boiling point is greater. And this way we can compare the melting points and boiling point of different compounds based on the lattice energy of the ionic compound. Okay, let's talk about a bit about covalent compounds then. In covalent compounds, covalent bond, I want to talk about covalent bonds which make the molecular compounds for us. For example, in the case of H2O, water molecule, we have covalent bond and this covalent bond exists between atoms inside a molecule. In molecular compounds we have covalent bond inside the atom. We have covalent bonds inside the molecule. So we have different types of molecule here. Some of the molecules are non-polar, some of the molecules are polar. And based on this, some changes we have some changes of boiling point and melting point. Okay, let me talk about polar and non-polar molecules. Polar and non-polar molecules. We can tell chloride Cl2, we have a covalent bond here which is between two chloride atoms, there is no electronegativity difference between these, so we can say this is completely symmetrical molecule, so this is a non-polar. There's no polarity in here. This is a non-polar molecule. But in the case of HCl, hydrogen chloride, chloride is more electronegative than hydrogen, so it will take a partial negative charge, and this is a positive partial charge, so it will be a polar molecule. In other cases, when we want to tell if it's a polar molecule or non-polar molecule, for example, let's think of CH4, which is methane gas. In room temperature, it's a gas. A carbon connected to four hydrogens, so it will have a tetrahedral formation. I'll draw it with edge and dash to show that it is three-dimensional, and the angles are 109.5, so it's not a planar molecule. All the bonds around the carbon are the same, so it's a non-polar molecule. It's a non-polar molecule. I can also tell it's a symmetrical molecule. From every side I look at this molecule, it is the same. CH4 is a non-polar molecule. So another example is CH3Cl. Okay, this single atom connected to carbon makes a difference. So because we have a different atom connected to central atom, we have a polar molecule, and here we have polarity. As a general rule, we can say a molecule is non-polar if it satisfies two conditions. So a molecule is non-polar if it satisfies these two conditions. One, has no lone pair, on the central atom. And number two is that all the atoms connected to the central atom are the same. Connected to the central atom are the same. Okay. As an example, for example, in the case we just reviewed, CH3Cl, different kinds of atom are connected to central atom. So condition number two is not satisfied, so it's not non-polar, so it is polar. It's a polar molecule. In other cases, for example, NH3, we know that in NH3, nitrogen has 5 electrons in the outermost shell, so it will make 3 covalent bonds with hydrogen, and it has a 1 lone pair. Because of this lone pair, it makes a polar molecule, because it's not symmetric anymore. If we look at it from the up here, it is different from if we look at from along a nitrogen hydrogen bond. It is different, so it's not symmetrical, it's polar. If we look at CO2 as another example, CO2 carbon atom, which is central atom, has no lone pair around it. All these pairs are bonding pairs, and both of them are the same. Both of them has Both of them are oxygen connected to the central atom, so it is a non-polar molecule. Both conditions are satisfied, so it is a non-polar molecule. Also, we can say that if we draw a vector called dipole moment, the dipole moment here is toward the oxygen, and the same, draw it more straight along this bond like this, and a dipole moment here exists like this, and these two vectors are aligned in a line, and the angle is 180, so these two vectors cancel out each other, their sum is 0, and that's why the molecule is nonpolar. Whenever the sum of dipole moment vectors is 0, we can say that the molecule is nonpolar. Okay, it's enough here.